Okay, my friends, you probably are wondering what happened to 3.6. And I got all stressed out and was wondering that too, and I realized that I don't go over 3.6. So I realized that I had 3.6 as something we were supposed to do on the sheet on the beginning here. 3.6 is something we're supposed to do, but that was a mistake. And so here's how you handle a mistake. Cross that out. I do also notice that in the homework that I've assigned that 3.6 is not there. And so what I'm going to go over right now is 3.7. Okay, 3.7, I'm going to have to delete these cartoons my son said off of my things because they're on YouTube. But okay, optimization problems. The first thing that you need to do, they're word problems. You need to read the problem. You need to list the knowns and unknowns. And the big question is, what do you want to optimize? Sometimes it's helpful to draw a picture and label things. And then you want to write an equation using only two variables. And it's nice if you can put what you want to optimize on one side equals and the expression with one other variable on the other side. Now, sometimes you can't get it with one other variable on the other side, and what you end up with is two variables on that side. Then what you want to do is you want to see if you can find another equation to get rid of one of those variables. Also, sometimes you can't get what you want to optimize all by itself, but if you can, that's really, really good. And so anyway, then you find the derivative with respect to this variable that you have on the other side. Then you find the critical points of that, because remember optimization, well, maybe I didn't say what optimization was, trying to find the maximum or the minimum of something. And so how we can find the local min or the local max or the absolute min or the absolute max is to find the critical points and check at the, and most of the time we're looking for the absolute max and absolute min, but it happens at a local spot. And also look at the, evaluate your critical points and your endpoints to see which one is the absolute min or the absolute max, whichever you're trying to find. And then you want to prove that the answer that you found, because a lot of times you only have one of these or maybe two things, and is it a max or did it go higher? You want to make sure, that it didn't go to infinity or anything like that. And so you can prove it using the second derivative test, and that just kind of makes it fun so that we can practice our second derivative. You could also use the first derivative test, and then you answer the question that they asked. And so we'll look at the next page here where I have some examples. So this is problem 18 from your textbook, and it says a farmer wants to fence a rectangular plot of land adjacent to a north wall of his barn. No fencing is needed along the barn, and the fencing along the west side of the plot is shared with a neighbor who will split the cost of the portion of the fence. Of that portion of the fence. If the fencing costs $20 per linear foot to install and the farmer is not willing to spend more than $5,000, find the dimensions for the plot that enclose the most area. Okay, so we have a situation where we have a barn. So here's the barn. And this is our plot out here that we're trying to fence in. So this is where I'm going to make my fenced in area there. And I'm going to be able to use this barn as part of the fence. So no fencing is needed there along the barn. And they said it was a rectangular plot. So to the best of my ability there, I've drawn a rectangle. I got a rectangular barn too, but my barn could have been more exciting. They have a neighbor that's on the west. Now this is what I would have to ask you guys. If north is up there, then east is over here. So I'm going to call this over here, this is the north, I'm going to call it, and I'm going to say this is the west. And if I'm wrong, please just go with it, because it doesn't matter which side. And I'm going to call that the east side over there. And so what we have going is that we have a person over here on the west side that will split the fencing with us, right? Is that right? the fencing along the west side is shared with a neighbor. This is not very well drawn. How did our neighbor get over there? Oh, okay. Well, just go with it. But that fencing over there is shared with the neighbor, and the other fencing he's going to have to pay for. So along the south side and the east side, he's going to pay for, and along the north, there's no fencing at all. Now, I want to come up with what am I trying to optimize, now I've got to figure out what I'm going to optimize here. Find the dimensions for the plot that will have the most area. So I'm trying to optimize the area. So my area is going to be the length of my times the width. Do you guys agree? And so I have what I want to optimize on one side, but I have two variables on the other side. So I'm going to try to get rid of one of those variables. So I kind of know, I'm going to call this the length, and I'm going to call this the width. And so I kind of know that this side will cost me $10 per foot. And if W is the number of feet, now the reason it's $10 per foot is that it costs $20 for the fencing per foot, and this farmer on the other side of us will share half and half with us. So this side over here is $10 per foot. So 10W plus, and then this side is $20 per foot because we don't have anyone who's going to share us. So 20L plus, and then over here, we don't have anyone that's going to share over here. So it's also $20. So $20 times W equals $5,000 altogether, because that's the most that he is willing to spend. Someone's texting me. I'm going to turn my texter off so that it doesn't ring again. Okay, and so when I combine like terms here, this is 30W plus 20L equals 5,000. And I'm going to solve for either L or for W, and it doesn't matter which one that I solve for. So this is half dozen each to the other. So whichever one I solve for, you're going to say, I would have done the other one. I'm just kidding. You wouldn't do that to me, would you? So 5,000, look, I caught that, minus 30W is going to equal 20L. And then I'm going to divide each piece by 20. So I'm going to get L equals, now 5,000 I think divides by 20 evenly. And so that's nice. So this is 250. And then that's minus, and I'm going to put 3 over 2W. And so if you were a 1.5W kind of guy, you could have that as well. Person, rather. Okay, so now what we're on about is we have this equation, and we know that L is this. So we're going to plug in. So I'm going to make a little G-jaw so that it fits. A equals, am I writing where you can see? I am. L, but we're replacing L with 250 minus 3 over 2W times W. And so the A equals 250W minus 3 over 2W squared. And now I'm going to find the derivative. Find, and I'm going to be finding dA dW. So when I take the derivative of A, that's dA dW, A prime if you want. And then when I take the derivative with respect to W of that, I get 250. And when I take the derivative of this with respect to W, the 2 comes down and multiplies by the 3.2 and gives 3. So that's minus 3W. And so my derivative equals 250 minus 3W. And I want to know, when is my derivative equal to 0? And when is my derivative undefined? Because those are where my critical values are going to be. Am I almost off of my writing? I don't know if you could see that. So A prime equals 250 minus 3W, A prime equals 0, and A prime is undefined. Well, it's not undefined ever, not. And it's 0 at 250 minus 3W. I put the 0 on the wrong side. How am I going to be so silly? 3W equals 250, or W equals 250 divided by 3. I don't think that goes evenly. And so there's our possible critical value. We didn't get a critical value for there. Now we want to also talk about, so this is a critical point, right? CP, critical point. And so we also want to talk about endpoints. And endpoints are going to go with, think about endpoints for W. Now, the lowest that I could go on W would be to have W be 0, but then it wouldn't make a rectangle. And so, and if W was like 0.1, it would make a really small rectangle, but 0 is the absolute of that, and it doesn't make sense as far as this problem goes. And then using all of my money just to put fencing in the W spots, however much fencing that would be, doesn't make sense either, because then L would be 0, and then you wouldn't have any area at all. And so the endpoints don't make sense here. So I did think about them. So this is my only possibility for the value that will make the maximum, right? Because that's what I was trying to maximize, right? Enclose the most area. This is what I'm trying to maximize. I'd like to maximize that. And so now I want to prove that this is a maximum value of that. So how you can prove that is by taking the second derivative. So I want to show, am I a place where you can see what I'm writing? To show that W equals 250 over 3 is a max of A. I want to show that. And let me see if you can see what I wrote. Okay, so what I'm going to do to show that is I'm going to take the second derivative of A, which is -3. And this was our critical point, remember, of A. And this, because it's negative, the second derivative is negative, is concave down, which means it's looking like this on the drawing. And here's our critical point right there. And so it's a max. You could also use the first derivative test by making a number line and whatnot. And so that would be another possibility for you to do. Now, we haven't answered the question that they asked, which is to find the dimensions for the plot that would enclose the most area. We found what W is, but we also want to find out what L is. So that's going to be our next story, is to find out what L is. Now, good news is that L is not going to be very hard, because right here we have an equation that tells us what L is in terms of W. So we're going to plug that in. So L equals 250 minus 3 over 2 times W, which was 250 over 3. Equals, and so this is going to tell us, and I'm going to put that all in my calculator, and you can do it by hand if you want, because I know a lot of you guys like to do things by hand. And I don't care. If you want to use your calculator on it, you can, and if you want to do it by hand, well, do it by hand. That'd be great. And that came out to be 125. And this, because it's a dimension, I'm thinking I would feel better if I wrote that as a mixed number. And so as a mixed number, and I could do that by hand too, this is 83 1/3. So the dimensions are 83 1/3. It was probably feet. I'm reading to see if it is feet. Yeah, linear foot, so it is feet, by 125 feet. And this is going to be the shared, that's going to be the side that we share with the other farmer. And so we want to make sure that people kind of know which one. And so one side is going to be shared with the other farmer. Have I made it where you can't see that? Of course I have, because that's how it's rolling today. So the dimensions are, in that 250 over 3, I converted it into a mixed number, 83 1/3 foot by 125 feet. And then I just noted that, hey, that's the side that we were sharing with the other farmer. Okay, so that's problem 18, and we did a pretty nice job on it. We did our best anyway. And I have other problem for you. These kind of rectangular problems are my favorite type of problems for optimization, because you can kind of visualize what's going on, and so I kind of like them. They have other problems in there, box problems and other things like that, and that's okay. Oh, did they ask me to find the area? Find the dimensions for the plot that will enclose the most area. It doesn't look like they asked me to find the area, but if they had asked me to find the area, that would be easy to find. All I'd have to do is multiply those two things together, right? Length times width equals the area. So if they had asked me to find the area, I could find the area, and I don't think that was in the directions. I think it asked me just to find the dimensions, but I want to choose. That's, you know, when they say answer the question they ask, make sure that you read carefully and make sure of. Okay, so this is problem 19, and it's talking about the same farmer, but instead he realizes that he wants to have, or she, I don't know, wants to have a different take on it. And so instead of having $5,000 worth of fencing, he wants to make sure that he has 8,000 square foot of land worth of fencing. So we still have his barn, and like I said, it really doesn't matter what sides, just as long as you kind of agreed to yourself. This is the shared side over there, and this is no fencing along here. So we said, remember that this was $10 per foot, right? And over here is $20 per foot. And just to keep the same thing going, we called this W and we called that W in the last problem. So let's do, this is $20 per foot over here because no one to share with. And this is L. So now, this time, what we're trying to do is we're trying to minimize the cost of the fence. And so you could use C for cost, and I'm trying to minimize that, the cost of the fence, minimize that. And how much the fence is going to cost me is 10W plus 20L plus 20W. So the cost of the fence is going to be 30W plus 20L. And again, the same thing. I have what I want to minimize or maximize on one side, so that's great. But on the other side, I have two variables, and I want to get rid of one of those variables. And these problems work out like this a lot. And what you're going to use is this 8,000. The area, which is length times the width, is supposed to be 8,000. So you can solve that equation very easily for either L or for W, and then you can plug it in, and you'll only have one unknown. So I'm going to solve it for L. It doesn't matter. Well, I guess I'm going to get W on one side, so I guess I'm going to solve for W. So 8,000 divided by L equals W, and now I'm going to plug that in right here for W. So C equals 30 over 8,000 divided by L plus 20L. And when I do a little math here, that's going to be 24, 2, 3, 4 zeros over L plus 20L. And to find the derivative of that, you could write this as 240,000, right? 2, 3, L to the negative 1 plus 20L. And now I'm going to find DC, DL is my goal. And so I'm going to check to see if I've written right off my paper. And miracles happen, I haven't. And so, and now what I'm going to do is I'm going to find the derivative. So when I find the derivative here, you can call it dc dl if you like, or you can call it c prime. Either way, I'm going to call it c prime. And then this is going to be negative 1 times that 240,000, L to the negative 2 plus 20, right? The derivative of 20L is 20. And so cleaning my derivative up just a little bit, this is negative 24,000, 240,000, just a slip of the tongue there, plus 20L. And remember, we're going to look where C prime equals 0 and where C prime is undefined. Okay, so now you can set that equal to 0 and solve it. So this is negative 24,000, ooh, I slip of the tongue again, over L squared plus 20 equals 0. So you can put the 20 over there. And multiply by L squared. Equals negative 20 L squared. And divide by negative 20. So we get L squared equals, and I'm going to go ahead and allow myself the grace of being able to use my calculator on that. So I got 12,000 equals L squared, and I'm going to take the square root of that, and I'm not going to worry about the negative because you can't have the length of your fencing be negative, right? So and so the square root there, I'm going to have the square root of 12,000, which is 20 square root of 30 exactly. This farmer's going to have to get out. My dad sometimes calls me and asks me about sizing on things. He builds a lot of stuff and whatnot, and I'll tell him an answer like that, and he tells me to the nearest 16th of an inch is what he says when I say that kind of thing. So okay, so we have this, and L is C prime is undefined when L equals 0, right? Because the denominator is 0, but that's not going to make sense as far as something I would need to test, because the length can't be 0. And so the critical value that I'm concerned about is this critical value, the 20 square root of 30. But this one, it doesn't make sense as far as the length of my fencing can't be 0. And for that matter, the width of my fencing can't be 0. So the endpoints don't make sense on this, so I won't have to look at them. So this is my only possibility, and I'm totally out of room, and I haven't planned very well. And for that, I apologize, but I'm going to make a spot right here. And what I want to show, make sure that I'm writing where you can see, I want to show that L equals 20 square root of 30 is a min value of C, right? That's what I want to make sure of. And I can use the second derivative test for that. And so I can come here where I have my first derivative, and I would like to do this so that I don't have to move it, right? And so, and take the second derivative. So C double prime would equal, and so this would be a negative 2 times a negative 240,000. So that's going to be a positive 48, 1, 2, 3, 4 zeros, right? And then that's going to be L to the negative third, and then the derivative of 20 is 0. So my C double prime is equal to 48, 4 zeros, over L to the third. And we're going to be putting L in as 20 square roots of 30. Now, I don't really care what the answer is here. So if you're thinking, oh my gosh, that's going to get nasty. Well, I agree with you. It is going to get nasty. But what do I care about? I care, is it positive or is it negative? That's what I care about. And because I'm looking for, is it concave up when the second derivative is positive? Is it concave down when the second derivative is negative? So it's concave up because this is positive, right? So it's concave up. And so that means that it looks like this, concave up, and this was a critical point. And so now we know that it's a minimum. Now I got to make sure that I answer the question of the problem, and the last part is that it's asking me what are the dimensions of the fence. And so I know what L is, 20 square root of 30 feet, and I want to find out what W is. So I'm going to answer that question right over here. I didn't plan very well, and I'm again, so this is going to be my answer. That the L is 20 square root of 30 feet. And of course you could give an approximation to that. And that W equals 8,000, remember, over L. Do you guys remember that equation that we had right here? And so we're going to use that. And so this is 8,000 over 20 square root of 30. And I'm not worried about, I mean, my calculator is going to figure that out and rationalize the denominator and do everything for me. And so I wonder if I could get it to do some dishes, because with all of us hanging out here at the house, our dishes have gotten out of control. So this is 40 square root of 30 over 3. So our W equals 40 square root of 30 over 3 feet. And if we wanted to know the area of the rectangle, which they didn't ask, we could certainly find that. And we could find the minimum cost as well. I was just checking to make sure that we had the right answer, because that would be silly for me to go with it if it wasn't the right answer. Okay, it was. On the next page, I have, if you'd like to read it, you can. It's about Kepler and how when he was getting married, he wanted to minimize the cost of the wine. And so I'm not sure that he was a cheapskate. I think it might just be that he was wise with his money. And so wine was kind of sold in a different way back then. And so you can read about that if you like. And so he kind of pioneered mathematics like this that would either minimize or maximize something. Okay. So I told you that 3.6 didn't get just forgotten, that I actually just messed up by having that. I'm not going to cover 3.6. If you're interested in 3.6, 3.6 is graphing with a calculator or with a computer, and then finding features using calculus. And I'm totally fine with you looking at that and working on it, but you're not required to have any kind of graphing device, and so that's the reason I don't cover that section. Okay, I'll see you later. I hope you guys are doing all right. I miss all of you. Bye-bye.